Hello math people, this is Mr. Ray with a lesson in our polynomial functions unit. We're going to try this lesson again. This is characteristics of polynomial functions. So the previous lesson we just kind of introduced ourselves to what is a polynomial function, what it looks like as a equation, and a few other things. Today we're going to dive a little bit deeper into polynomial functions. So a few definitions here. These are going to be new, mostly. Now, up till now, we've only been dealing with polynomial functions really up to degree 2, so basically linear and quadratic. Quadratic functions either had a minimum or a maximum point. Okay, we call those optimal points. Now, once we get to a degree 3 or higher, we start developing some more interesting points. For example, if I was to draw like a typical polynomial function, they kind of look like roller coasters. They've got lots of peaks, or they could have lots of little peaks and valleys. Now, what happens at the end, and we're going to talk a lot about this, is as the function goes to the extreme right, meaning very high positive values of x, the function will either head off to positive infinity or down to negative infinity. Okay, and the same behavior at the end. So it's not going to end up in like a straight line or go towards an asymptote. It will definitely be heading towards positive or negative infinity on both ends. We call that end behavior. Now, in between that, for example, I could say, well, here's a function and I know it's going to head towards positive infinity as x gets increasingly large. That means y is getting increasingly large, of course. Down here, as x gets more and more negative, y approaches or heads towards negative infinity. Now, in between here, we can have all sorts of, like I said, peaks and valleys, something like this. So that could be a typical polynomial function. So if you look at this, well, this actually doesn't have what we would normally call a maximum or minimum, because there is no maximum, because it heads, you could get a y value of any possible high positive value you want, because it just keeps on going up. Same thing in the negative direction for y. There's no value you could say that all y values are less than or greater than these. So, but there are some interesting points here. You could say, well, that sort of looks like a maximum, that sort of looks like a minimum, etc. So we kind of differentiate. We have two types of mins and max now. So we have these things called local minimums, and local maximums. We also use the term relative, okay, but local is the term that I prefer, but you might see this in textbooks or other videos. So the local mins or max, this function actually has a few of those, even though it has no highest possible value of the function or lowest possible value of the function. These values here, where it changes direction from going from positive to negative, these are all called local. You could call these local extrema, because this would be a local maximum. You can see on the left it's heading down, on the right it's heading down, so it's heading up towards it and then changing direction going down. Same thing over here. These two are local maximums, these two here, and these two are local minimums, because for a very for a small section of this function, you can see that in that area this would be the maximum value, this would be the maximum value of this area, and so on. So anytime it changes direction within the function from positive to negative or negative to positive, we call those, well, we actually have a name for those. Those are turning points, but each turning point is either going to be a local min or a local max. Okay, so that's kind of new for these polynomial functions. We didn't have these with quadratics, and certainly not with lines. Okay, now the old definition of a min-max, we now kind of preface that with the word global or absolute. So that means for the entire function, the entire range of x values, a global min or global max would be the highest or lowest for the entire function, like a vertex is. Okay, and I've already mentioned turning point. Turning point is wherever the function changes from positive to negative or negative to positive. So the turning points are where the local mins and maxes are. Okay. We also have this term here, a leading coefficient. So we know a coefficient is what's the number that multiplies with the variable part. So for example, if I just came up with a random equation of in this case it's a quartic, so it's degree 4 plus 2x squared minus 13. So that's just random, I just picked that out. So now we know this is a degree 4 because that's the highest exponent of the three terms. Okay, so whatever term has that highest exponent, we call that the leading term, and whatever the coefficient is of that leading term is called the leading coefficient. So in this case, the leading coefficient is -3. Okay, so it's not always the first term. As long as you've got the terms sorted from highest degree exponent to lowest, it will be the first term, but you just have to be careful to make sure you're actually picking the term that is the highest degree term. Okay, so we're actually going to use the leading coefficient to talk about some of the behavior to make some predictions. So that's where you will get that from. Okay, so this lesson probably has the most key concepts of any lesson in high school. I think it's pretty, it's not even close. So there's a lot of stuff here. I'm going to try to group it together so you can kind of refer to it later on in terms of categories or groups of related concepts. Now the first thing is this third one, I've actually duplicated that later on for some reason. So we'll take that one out, not to confuse you. So the first two, just kind of some basic quick definition here. Polynomial functions of the same degree have similar characteristics. So what that means is any polynomial function that has the same degree, the leading term has the same exponent. For example, this function here would have certain attributes very similar to another function, g of x equals 8x to the fourth. Okay, as long as x to the fourth was the highest degree term, or at least the highest degree, they're going to share some attributes, and we're going to learn about that later on. Okay, this one here, polynomial function of degree n has at most n turning points. And that's kind of interesting because you can basically look at the degree and say, well, that function can only have so many turning points. So you can use that to your advantage. You could look at a graph. For example, if I went back to this graph, this has 4 turning points. Okay, so this has to be at least degree 5. Because for it to have 4 turning points, then n would have to be at least 1 higher than the number of turning points. Okay, so it could be degree 5 or degree 6 or higher. Okay, but you could never say, well, that's a x cubed, that's a cubic, or certainly not a quadratic or a line. Okay, so you can kind of use the number of turning points to predict the possible degree. Okay, and vice versa when you're going from the equation to the graph, you can use that knowledge. Okay, now the next few here, so I'm going to group all these guys down to here. Okay, so these concepts all have to do with the domain and range. So I'll just put a DR here. Okay, so the domain of all odd degree polynomials is x can be any real number. So basically, and we already know that's true. This should be nothing new. We talked about last lesson how the domain of all polynomials is all real numbers. So nothing earth-shattering here. But also, this is pointing out if the domain, if it's an odd degree polynomial, the range is also every possible number. So y can be any real number, x can be any real number for the domain. Okay, so the easiest one to look at for this would be if you had a line. Okay, I'm just gonna end up. So if that's my linear equations, that might be like y equals x plus 3. Okay, in terms of domain and range, you can see that this is going upwards forever, to the right forever, downwards forever, and to the left forever. You can see that a degree 1 equation, a linear equation, the y values and the x values have all possible real numbers. Okay, and this is true. We're going to see that this is true with a third degree equation, a cubic, or fifth degree equation, a seventh. So any odd degree polynomial will basically go up forever and go down forever for the y values. Okay, but if you had, so that's pretty straightforward, right? If the degree is odd, x and y can be any number. Okay, but as soon as you change it to even degree, so the simplest even degree polynomial we know about is a quadratic, which makes a parabola on the graph. Okay, so if that's your parabola, you can see for all parabolas, well, the domain is going to be all real numbers, which we also knew from before. So x can be any number, but the y value is restricted by the vertex. So in this case, the y values are only greater than or equal to this point A, this value A here. Or if it opens down, it would have to be less than or equal to that value. Okay, so this is going to extend for all even degree functions. So if it's x to the 4th, x to the 6th, you're still going to have this restriction on the range. You don't have any restriction on the domain. So that's how that works. Now, we talked about the leading coefficient, okay? And we kind of know this for quadratics from grade 10, 11. If your leading coefficient is positive, okay, and you have an even degree function, so this would be an example of a positive leading coefficient. This might be, well, I don't know really, but it might start with, say, 2x squared. Okay, positive 2x squared. Remember, when a is positive for quadratics, it's going to open up. So that leading coefficient will determine the minimum of the function. Okay, if the positive leading coefficient of a quadratic was negative, it's going to open down. And so that will determine this point here in this case would now be a maximum for the function. So that would restrict your domain to be any values of y less than or equal to that value of a. Okay, and this would extend to degree 4, degree 6, degree 8, etc. Okay, so you will always have, and when we say minimum and maximum here, these are global minimum and maximums. Okay, so you will always have a global min and a global max for a degree, even degree polynomial, and whether it's a min or max depends on the leading coefficient. So if it's negative, it'll be a maximum, global maximum value. If its leading coefficient's positive, it'll be a global minimum value. Okay, so that talks about domain range. Hopefully you can see. It's nice It's nice when it's odd degree because basically there's no restrictions on domain or range, but this kind of breaks down for the even degree polynomials. Okay, so min max. I mean, we've been talking about this as we've been talking about domain range, so this should not be. This should come naturally at this point. So an odd degree function, odd degree functions have no global max or global min. Okay, so remember this is our simplest odd degree function. There's definitely no global min or global max here. It just keeps on going up and down forever. And that, like I said, that extends to cubic, degree 3, degree 5, degree 7. Okay, so that's odd degree. An even degree polynomial with positive leading coefficient will have at least one minimum point. So when we say at least one, we're talking about combined global and local min-maxes combined. Okay, an even degree polynomial with negative leading coefficient will have at least one maximum point. We've talked about that with these examples here. Now, the next few concepts, okay, the one at the bottom of the first page and the next two at the top of the second page, these have to do with symmetry. So I'll write symmetry here for this one since there's a couple of them. Now I'm not going to discuss, I've decided I'm not going to discuss symmetry in this lesson, even though I've got the concepts here. So what I'm going to do, I'm going to discuss that separately when we meet, kind of as an additional learning. Just I feel there's quite a bit to talk about in this lesson. Let's leave that till later. Okay, so the next two have to do with x-intercepts. Now remember we kind of have a few words for x-intercepts, and you're going to see this show up in homework questions and the textbook and other videos. So I usually call them x-intercepts just because, you know, it's a follow through from the previous grade math courses. But we can also, I'll just show it here, we could also call those zeros, and we can also call them roots. Okay, most of the time I'll call them x-intercepts or zeros, but if you hear any of those three, in terms of polynomials, all three of these are going to be the same. Okay, so now that you know, understand the x-intercept part, an odd degree function has at least one x-intercept and up to a maximum of n intercepts. Okay, so that's odd degree. So again, if we went back to the simplest odd degree function, that would be a line. Okay, and we've already talked about how basically odd degree functions stretch from y being up to positive infinity down to negative infinity. So that tells you that it basically, that polynomial has to cross the x-axis for sure in order to go up to the highest possible y values and then extending down to the lowest possible y values. It has to cross at least once. Okay, so if I was to look at, you know, if this was a linear function degree 1, this is telling me that that line, which is a specific odd degree function, has at least one x-intercept up to a maximum of n, and n in this case, the degree is 1. So it has to have at least one up to a maximum of 1. So that tells you all lines have exactly one x-intercept. Okay, if we went up to like a cubic where it has an x cubed term, that would tell you, and again you have the same issue, it has to have at least one because it's going to cross through the whole spectrum of y values. So at least one up to 3 intercepts. Okay, it could have only one, it could have 2, or it could have 3. So there's no, unlike a line that says that there's always one, cubic will have anywhere from 1 to 3. A degree 5 polynomial would have anywhere from 1 to 5 x-intercepts, and so on. Remember, n is the degree. Okay, even degree is a little different. So if you remember, now I'm going to draw a couple of quadratics here. So here's one, right, and here's another one. Now, I can draw another one too. Might be a little messy. So if you remember from grade 10, this quadratic has 0 x-intercepts. Okay, because it actually doesn't extend past the x-axis, so it has 0. The one here, this is probably the most common. It has 2 x-intercepts. So this one's 0, this one 2, and this one where the vertex is right on the x-axis has 1. So you already kind of knew that a quadratic can have anywhere from 0 to 2 x-intercepts, and that's confirmed here. So an even degree has from 0 to a maximum of n x-intercepts. So for quadratic, n is 2. So from 0 to 2 x-intercepts. So if you extend this to other other even degree functions, a degree 4 will have anywhere from 0 to 4. Degree 6 would have anywhere from 0 to 6, etc. Okay, so I'll just put a little note here for future reference for you. X-intercepts are there. Okay, and for any polynomial function of degree, okay, this has to do with looking at the table of values. So it's a little confusing when you read this. But if you remember, when we had a table of values of a linear function, we looked at the first differences, and they were always constant. So if you just had a table of values, you didn't know what kind of function it was, you could do the first differences, and if they were all constant, you knew it was linear, even without seeing the equation or the graph, or graphing the points. So you knew that from grade 9. Then grade 10, we looked at quadratics. So if we looked at the table of values and the first differences were not constant, you took the second differences, and if they were constant, you knew that that relation or function was quadratic. Okay, now we're going to extend that because now we're looking at polynomials of degree 3 or higher. So if we did first and second differences of a table of values of some unknown relation, and they were not constant, then we could then look at the third differences. That's taking the differences of the second differences. If they're constant, if the third differences are constant, we know the degree is 3, and that just continues on forever. If you looked at the fourth differences and they were constant, it's a degree 4, and so on. Okay. Now this last part here has to do with determining the leading coefficient. So rather than try to explain something very new to you here, we have an example on the last page. So I'll explain this concept and you can go back to it later. So this has to do with looking at the table of values. So the differences. Okay, so this graph here, or this table, is a very useful learning tool or reference piece of information. So it's a table, and just to get your bearings on how this is organized. So at the top here, we've got the first section, odd degree polynomials, and then even degree polynomials over here. And then we break each of those into the leading coefficient, positive or negative for odd, positive or negative for even degree. Okay, and then we talk about certain characteristics. So the first thing we talk about is the end behavior. Okay, now, so basically, if you had, this is an example of an odd degree polynomial with a positive leading coefficient. Okay, now what I'm going to focus on here is what's happening at the end, or what's the end behavior. So you can kind of see where these functions are heading off into the distance on the left and right side. So what this is saying is all odd degree polynomial functions with a positive leading coefficient, for example, y equals 3x cubed, would have this same behavior at the ends. Okay, and that end behavior is listed here. Okay, so this is basically as x approaches negative infinity, so as x goes that way, y is approaching negative infinity, it's going down. Okay, and as x approaches positive infinity, as it goes to the right, y is also approaching positive infinity. So this is one way of talking about the end behavior. There's a couple other ways that I think are a little more practical and easier to use. And that this one would, the first one is just showing arrows. So if I was just to summarize the end behavior, I would draw an arrow in this quadrant going up and an arrow in this quadrant going down. So all odd degree polynomials with positive leading coefficient will have this end behavior. So, and there's another way to talk about this, and that's using the quadrant numbers. So instead of drawing a picture here, so if you remember, hopefully, we've named the 4 quadrants just so you can identify them quickly. So we start here, that's quadrant 1, and then we go counterclockwise, quadrant 2, quadrant 3, quadrant 4. So for example, this end behavior, as we go left to right, starting in quadrant 3, and it's ending up in quadrant 1. So that's how I would describe the end behavior. It's quadrant 3 to quadrant 1. Starts here, ends here. Okay, so you can use any of these 3. You could use the quadrant methodology or way of describing it. You could put the arrows here, or you could use as x approaches negative infinity, as x approaches positive infinity. Whichever one you like the best is acceptable for me. Okay, if we now go to an odd degree polynomial, this time with a negative leading coefficient, you're going to see all those types of polynomials will have this. It won't look exactly like this, but the main thing we're looking at is what's going on at the end behavior. So you can see what happens. Basically, this when you change the leading coefficient from positive to negative, it basically flips upside down. Okay, so when it flips upside down, basically now instead of being in this quadrant, it's here, it starts here, and instead of ending in this quadrant, it ends here. So it's exactly the opposite. So if I was to draw the picture here, I would now say, okay, it starts here and goes down here. And then in terms of the quadrant, starts in quadrant 2, ends in quadrant 4. So quadrant 2 to quadrant 4. Okay, now, so that covers the odd degree polynomials. You can see they have certain end behavior characteristics that are in common depending on the leading coefficient and the fact that it's odd degree. If we move to even degree, so a positive leading coefficient, and you could just think about the most basic even degree polynomial with a positive coefficient, and that would be a quadratic opening up. It has the same end behavior as this. So basically it's, this is opening up as well. And in both directions, they're heading off to, y is heading off to positive infinity. So if I was to draw my quick sketch of the directions, they'd both be heading up on the top. Okay, and that would be quadrant 2 to quadrant 1. And finally, if it was a even degree polynomial with a negative leading coefficient, and you could think about, say, y equals negative 2x squared, it opens down like that. So it has, again, the exact opposite behavior. So they're both going towards, y is going towards negative infinity on both sides of the x. So in this case, we've got our arrows going down, and that would be quadrant 3 to quadrant 4. So that's the end behavior characteristic. So that's going to be important because you can, you could either look at an equation of a polynomial and directly know what the end behavior is from that by knowing is it odd degree or even degree, and is the leading coefficient positive or negative? Okay, and then you could also look at a graph, get the end behavior, and say, oh, that must be an odd degree with negative leading coefficient. So you can work in both directions with this knowledge. Okay, domain and range, we've already talked about this. Any odd degree polynomial has the domain can be any real numbers for x, and the range can be sorry, this is just domain, sorry. The domain for both of them, any real numbers. The range, if it's a odd degree, y is any real number, and this is the case where we basically have a global min or max that kind of restricts the range. It has to be either greater than or less than that point, or less than or equal to that point. Okay, and this just talks about what I just said here. So no max or min, and this would always have a when we talk about minimum here, we're talking about global minimum. This has a global minimum, this has a global maximum. Okay, so that's a useful chart, just getting used to this. I think by the end of the unit, you won't have to refer to this. It should just come pretty natural to you. Okay, so we're going to get into some questions now. Some examples. So this one is match the polynomial function with its graph. So this is what I was just talking about. So looking at the equation, we now know something about it. We know the end behavior. And let's see what else we can figure out. Okay, so in this case, so 2x cubed. Okay, so what we know right here is leading coefficient's positive and the degree is odd. So I'll just refer to the chart for this one question. The rest of it we'll just know. So in this case, we have odd degree, positive leading coefficient. So that is this case here, the first column. So we know that the end behavior is Q3 to Q1, or this. So right away, as soon as I see that, I can say, well, I know the graph will look something like this. Move that back over. So that's what we just drew on the last chart. We know that. We also know a couple other things. So we know something about the x-intercepts. So remember, when it's odd degree, it has to have at least one. So it has at least one, and the maximum will be the degree, so somewhere between 1 and 3. Okay, the turning points. Okay, now I don't think we listed this on the key concepts, but if it's odd degree, it doesn't necessarily have to turn at all. Okay, so because it could be degree 1. So I'm just going to put here 0 up to, and the number of maximum turning points is always 1 less than a degree. So anywhere from 0 to 2 turning points. And the last thing I want to put here is the y-intercept. We haven't talked at all about that. Now, if you remember working with linear functions and you had your equation y equals mx plus b, you knew that b was the y-intercept. And then you took quadratics and you had y equals x squared plus bx plus c. You knew that c was the y-intercept. Well, that pattern continues. So the constant term in any polynomial function will be, in any polynomial equation, is always the y-intercept. Okay, so we know what the y-intercept is. So y equals 1. So now we can, there's only 4 choices here and they're pretty different. I kind of went overboard here with grabbing as much information as we could. Let me just zoom out a bit here. You can see the whole thing. Okay. All right, so first thing I'm going to look for is just pare it down very quickly because this is quite visual. Something that kind of goes in that direction. So I'm just going to put my, my pencil across. So it has to start here and end here. Well, that doesn't work. Start here, end here. No, that's the exact opposite. Start here, end here. Nope. Start here, end here. Yes. So right away, just by looking at the end behavior, by itself, we know that this is the only possible, this is the only possible graph that works for that equation. So let's just look at the other characteristics that we noted up here. Has between 1 and 3 x-intercepts. So if we counted them, not exactly sure, but it looks like it has 3 x-intercepts, possibly 2. So that's okay, that fits there. Turning point 0 to 2, so there's a turning point here and there's a turning point, so that matches our information. And a y-intercept of 1, well, this has to be exact, and it does have a y-intercept of 1, so that matches all our information that we put down. So it's definitely this graph here. So that matches up with graph 4. So I don't have to look at that one again. Just so you note, I've kind of got these out of order a bit. So this is 1, 3, 2, 4. So these two are kind of switched, but as long as you identify them, you're fine. Okay, the next equation, it's again, all we're really looking at is 3 things. We're looking at the leading coefficient, it's negative. We're looking at the degree of the leading term, that's the degree of the equation, that's 4, so that's even. And the y, or the y-intercept we know is going to be 4. So if I looked at these 2 things, even degree, negative leading coefficient, I always think about the simplest even degree with a negative leading coefficient. I think about, say, negative x squared. Okay, and I know that opens down. So that's a quick way to remember. And the odd degree, you could think about a line. So if you had a line, you know, you could get the end behavior without even referring back to those notes. Okay, so we know the end behavior here. So that's the x-intercepts. So remember, when it's even degree, it doesn't have to have, it could have 0 x-intercepts because it doesn't necessarily have to cross, and it can have up to n, the degree, so it can have up to 4 turning points. Now, we didn't really discuss turning points a whole lot, but when it's even degree, it has to have at least 1, because it's changing from, it definitely has to do a turn here and come back, or if it was up here, it would have to turn. Okay, whereas the turning points for even degree, if you did this end behavior, you say, well, it doesn't necessarily have to turn. So that's why we could put 0 here, and we put 1 here as the minimum, and it goes up to a maximum of 3. Just like, so the maximums are the same for the turning points, but the minimum is different. And then the final thing is the y-intercept. We know that's -4. Okay, so if we looked at the end behavior, it should be opening down on both, and right away we see that this one does, none of the other ones do, so it should be this one. Let's just confirm from our other information. It's between 0 and 4 x-intercepts, 1, 2, 3, 4. So that's okay. Turning points, 1, 2, 3, that fits in there, and a y-intercept of -4. Yes, because the scale is a little more compressed, that is -4 there. So this is our graph. So that's graph number 3 for that one. Okay, so hopefully you're getting the hang of this. This time the equation -2x to the 5th. So we're looking at leading coefficient is negative. The degree is odd. And this time, don't fall into the trap of thinking it's -1. The constant is 0, so that's going to be your y-intercept. Okay, so negative leading coefficient, odd behavior. So in this case, I'm thinking of the smallest degree odd function. That would be degree 1. That's a line. So what would the graph of y equal -x look like? That's kind of what I was talking about with the last one. What's a quick, easy way to remember? So -x would be coming from the top down to the bottom. Okay, and you could also use your chart from the previous page. Okay, so that's the end behavior. X-intercepts, it's going to be, so this time because it's odd, it has to have at least 1, and it can have up to 1 less than the degree. Sorry, it can have up to the degree, so 1 to 5. And the turning points, it can have, so this time, so an odd degree doesn't necessarily have to have any turning points, and it can have up to 1 less than the degree, so that's 0 to 4, and the y-intercept is 0. Okay, so not a whole lot to look for here. That doesn't match up because of the end behavior. Hold on. What did I do here? Okay, so I matched this one wrong. This is supposed to be, that should be this one because of the end behavior. That's the one we were looking at. I just crossed off the wrong one. Sorry about that. So this one is gone. This one is still an option. Okay. All right, so now when we're looking at this, we're looking at this end behavior. So basically coming down like that, and this has the same end behavior. Okay, let's match up x-intercepts. This one, it's hard to tell, but 1, 2, 3, 4 could be 5, maybe 4. So that fits in with that range, that possibility here. Turning points, this one has quite a few. So 1, 2, 3, 4, that still fits. Y-intercept of 0, that works as well. So this graph matches up to 3. This one was 1 from earlier. Okay, so that takes care of this one. Okay, and pretty sure we know what the last one is, but let's just go through the steps. Okay, so this is, there's no leading coefficient here, so it's a positive 1. So you can say the leading coefficient is positive, and the degree is even, and there's your y-intercept. So even degree, positive leading coefficient. You could think of the simplest example, even degree quadratic. So x squared, y equals positive x squared would have this end behavior. Okay, and that will match up to what we did on the previous page as well. X-intercepts. So remember, because it's even degree, it doesn't necessarily have to have any. It could have 0, and it's going to have up to the degree of 6 x-intercepts. Turning points, it has to have at least 1 because it has to turn, and it can have up to 1 less than the degree, and the y-intercept is 3. Okay, so surprise, surprise, the only one left is this one that matches the end behavior. In terms of x-intercepts, 1, 2, 3, 4, that's inside that possible range of values, and turning points 1, 2, 3, that's okay, and y-intercept is 3, that matches as well. So this is definitely graph number 2. Okay, so hopefully that exercise makes sense. How you take the equation, you can get quite a bit of information about what the graph might look like or not look like, based on looking at the leading coefficient, whether it's positive or negative, the degree of the polynomial function, and also the constant term tells you what the y-intercept is. Okay. Okay, so on the next page, this time there's no graphs to match. So what we're going to do is look at we're going to describe the end behavior, which we did in the last example as well. Also the possible number of turning points and zeros, so remember zeros as x-intercepts. Use these characteristics to sketch possible graphs of the function. I'm going to go a step farther. It doesn't say anything about the y-intercept, but we'll use that as well. Okay, so this is really similar to the last example, except we're going to create our own possible graph. Okay, it won't be the exact right graph, but I mean, if you plug this into decimals, you'll get the exact right graph, but we're just looking to get a really rough sketch of what this could look like. We're gonna, we're gonna add to our information as we go in through the next couple of units to get even more information than we're using now to get our graph much more accurate. Okay, so if we were to look at this, we have a negative leading coefficient, we have an odd degree polynomial, and there's our y-intercept. So our end behavior, again, you can use your quadrant, or you could use your as x approaches negative infinity statements, whichever of those three resonates with you the best. That's what I want you to do. Okay, so we know odd degree odd degree negative leading coefficient, so that would be like y equals negative x, a line, so we know it looks like that. So in terms of, I'm going to call them x-intercepts even though they said zeros here. The x-intercepts, it has to have at least one because it has to cross the x-axis, and it can have up to the degree, so that's 5. Turning points, it doesn't necessarily have to turn, even though that's really not true. So I'm going to say, but I'm going to say 0, not actually using that number yet, just the fact that it's odd. We're going to say from 0 to 1 less than 5. Okay, and then the y-intercept is negative 5. Okay, so now we're actually going to create a potential sketch of a graph that looks something like the graph of this function. Okay, so I'm going to kind of just pencil in, the ends of the function based on the end behavior we know. And I'm going to touch this up to make it look a little more realistic. So we know the y-intercept is negative 5. So got our negative 5 here. Okay, now let's make sure we use these rules. So it has to have at least one x-intercept. It can have up to 5, and it can have anywhere from 0 to 4 turning points. So I'm going to, and this is where you can be a bit creative, so I'm going to start here and maybe make this a little steeper. I'm going to have this come down, come up here, turn back down, cross through here, go back, and then come down here. Okay, so that matches. Well, we don't know for sure. So the intercept's okay, and behavior, that we already started with that. So the x-intercepts, how many do we have? We got 1, 2, 3. So that's fine. Turning points, we got 1, 2, 3, 4. So that's the most it could have, but it's still okay. So that is a potential sketch. You could come up with your own. You could have more or less x-intercepts, or more or less. I guess you couldn't have more turning points, but you could have less turning points. So this is not the graph of this function, just to let you know. We're just kind of coming up with sketches based on the three things we're looking at: the leading coefficient, the degree of the polynomial, and the y-intercept. Okay, so we're not even really looking at the number and the middle part of this function. Okay, so let's do this one more time. So this time we've got g of x, so that's a negative leading coefficient. The degree is 4, so that's even degree, and there's our y-intercept. Okay, so polynomial, even degree polynomial with, so that's like a parabola, to take a simple example, and negative leading coefficient means it opens down on both sides, something like that. And the x-intercepts, so we know with even, it doesn't necessarily have to have any, so it can be from 0 to the degree 4 x-intercepts. Turning points, it has to turn at least once, just because of the end behavior, and it can have up to 1 less than the degree, so between 1 and 3 turning points, and the y-intercept is equal to negative 4. Okay, so we'll use that to create a possible sketch. This is really rough. Hope you're getting the impression. I can't emphasize that enough. We're just kind of coming up with the attributes, not necessarily a perfect graph. Okay, so in this case, we've got the y-intercept of -4. Our end behavior it's down in those quadrants. Okay, in terms of x-intercepts, it doesn't necessarily have to have any, but it could have up to 4. So I could keep this graph entirely below the x-axis, but I don't have to. I could actually, I'll go crazy and make it actually have the maximum numbers. So it comes down here, back up, and then comes back down. So that's a potential sketch of a polynomial even degree negative leading coefficient with that y-intercept. Okay, so want to make sure you understand it. I know I'm repeating this way too often, but that's not an exact graph of this. This is just coming up with some characteristics of what the graph would look like. Okay, last page. All right, so this is a little different. We don't have the equation. We're just given some characteristics. So it says, what could the graph of a polynomial function that has a range, y is a real number, y is less than or equal to 10, and 3 turning points look like? What can you determine about its equation? So we're going to start right off by drawing a possible graph. So the fact that the range says it's less than or equal to 10, so if I have my 10 up here, I know the entire function, it's actually going to hit a y value of 10 because it's also equal to 10, but everything to the left and right will be below. So that tells us that this, it's for sure it's going to be approaching negative. The range is approaching negative infinity on both sides. Now, if I just do like a little, this is an asymptote or other, this is just reminding me where I have to stay below. Okay, so it says it has 3 turning points, so I have to make sure we turn 3 times. So I'll just kind of build this as we go. So if I go up here, there's 1 turning point, 2 turning points. Now this time I do have to go up to here and turn right at y equals 10 and then come back down. Okay, so if we want to make sure the domain is less than or equal to 10, that's true. What else? It has 3 turning points. 1, 2, 3. So that matches. Okay, so not a lot of information. There's a potential sketch. So what do we know about the equation? Well, we're able to determine the end behavior had to be going from quadrant 3 to quadrant 4. So that tells us, first of all, we have a negative leading coefficient because of that. In terms of the degree, we know it's going to be even degree because there's a couple of things that tells us that. One is the fact that there is a maximum value, okay, and also the end behavior tells you that as well. What do we know about the degree other than the fact that it's even? Well, remember the turning points. The turning points had to be, so if we note that there's 3 turning points, that tells us the degree has to be at least 4. It has to be at least 1 more than the number of turning points. So from the turning points, we know the degree is greater than or equal to 4. So that rules out 2 because up to this point we said, well, maybe it's degree 2. You can look at this and say, well, that's obviously not a quadratic, but you can also tell that by the number of turning points. And the fact that we know the number of turning points is always 1, it can't be any more than the number of than the degree. Okay, so that tells us, if we put these two together, that the degree is 4, 6, 8, so on. Okay, now what about the zeros, or the x-intercepts? So now remember, the number of zeros was the maximum so since there's 3 turning points, if we look at it, what's the maximum number of times it crosses here? 1, 2, 3, 4. But we kind of just drew that arbitrarily, so that for our graph it might be 4, but it's actually 2, 3, or 4 zeros. There's quite a few options here depending on how we drew it. The fact that the maximum was up here means it has to have at least 2, because at the very minimum, like ours, it has to cross here twice to get down to negative infinity. Okay, but there could be 2 more. Like if we drop this down here, there'd actually be 2 more, and there could be 3 if we just dropped this down and touched. So 2, 3, or 4 would be the maximum. So you can relate the turning points to the number of zeros, or x-intercepts. And do we know anything about the y-intercept? Well, not really. I kind of arbitrarily drew it here. It could have been anywhere below or including y equals 10, because maybe the maximum was right on the y-axis. That's possible. So we do know that the y-intercept is less than or equal to 10. Okay, and that's I think that's all we can tell. But I mean, just by basing on the fact that we knew what the range was and we knew what the number of turning points, that's actually kind of surprising that we can get that much information from so little given to us. Okay, last question, and this is I talked earlier on about the finite differences, the first differences, second differences, and so on, and the fact that we can now extend beyond second differences. So for example, if we had a table of values and the first and second differences were not constant, we could keep going, do the third differences. If the third differences are constant, you know the degree is 3. Okay, so we'll start off by doing that, and then these 2 things that we want to find out, that was the part that I said I'd talk about later when we did the key concepts. So I'm just going to start now with the differences. So there's a lot of differences here in these 2. So I'm just going to I'll show you how to do the first couple, and then I'll just write the rest in to save some time. So remember, the differences, you see, well, how did it change going from negative 36 to negative 12? So in order to do that mathematically, you take the lower one and subtract the higher one in terms of on the table of values. So negative 12 minus negative 36, that's the same as negative 12 plus 36, so that's positive 24. And if we keep going, we got plus 10, plus 2, 0, plus 4, plus, what is that? Plus 14, and then plus 30. Okay, so looking at that, you can obviously tell, well, it's not linear. You could probably tell that by quickly looking at it. So let's go to second differences. Okay, so this would be like 10 minus 24. So start off with minus 14. Then you go to minus 8, minus 2, plus 4, plus 10, and plus 16. So again, second differences are not constant, so therefore this cannot represent a quadratic relation or degree 2. So we keep going. So this is the first time we've ever done this. Go to third differences. So in this case, negative 8 minus negative 14, negative 8 plus 14, that's plus 6, negative 2 plus 8, 6. So you can see all these actually work out to being plus 6. Okay, so we have 5 of those. Yeah, so these are all constant. So we know this is a degree 3. So the answer to the first question, the degree equals 3. So that tells us the leading term will have an x cubed in it. Okay, now the second part here, I didn't explain this, how to get this yet. So there's a formula that we use for this. So I'll explain what the different variables mean. So c is equal to a times n, and it's an exclamation mark. So this is probably something you haven't seen. This is actually a button on your calculator if you want to try it out. So this is called factorial. So n factorial. N is the degree. So we now know what n is. So what do these other things mean? Okay, well c is the constant. So this value here tells you that c is equal to 6. N is equal to 3. And what we're trying to figure out is what a is. So what is a representing? A is the leading coefficient. So you can see by knowing what the value of the constants were when we got to the final part here, the final finite difference. So n factorial, what does that mean? What does factorial mean? Okay, so the way we do factorial, so for example, I'll do 3 factorial. 3 factorial is you start with the number that's here, and then you just keep multiplying by each integer below, 3 times 2, and you stop when you get to 1. Okay, so 3 factorial is equal to 3 times 2 times 1, that's 6. 4 factorial would be 4 times 3 times 2 times 1, which is basically multiplying this by 4, so that's 24. So those are some examples of using it. Okay, you can just imagine if you had a big number like 16 factorial, it gets big very, very fast. Okay, we use factorial if you're taking data management. This is a very common thing that we do in data management for getting probabilities and when we count the number of possible things that can happen. Okay, so how do we use this now? So to answer B and C, the sign of the leading coefficient and the value, they kind of, I don't know why it's in 2 separate parts here. Let's get the value, and then from the value we'll get the sign. So we know that C is equal to A times n factorial. That's the formula from here. So let's plug in what we know is the constant. C is 6. A is what we're trying to find. And n factorial, in this case it's 3 factorial. 3 factorial is 6. So 6 is equal to 6 times a, so that's very easy. So the leading coefficient is equal to positive 1, so that means the leading coefficient is positive. Okay. All right, let's do one more example now that you've seen how to do this. So this one here. Now, one thing I wanted to point out, every time you do the next finite difference, you notice you get one less value than the time before, right? So this time we had 5 third differences, we had 6 second differences, 7 first, and we actually had 8 in the table. So you have to have in order to get this to work, you have to have a certain number of points. Like you couldn't just look at 3 points or 3 rows in the table of values and be able to do fourth differences. That's never going to work. Okay, so that's why there's so many points here, is because you need a certain number of points. Okay, so if we're looking at this, if we did the first differences, now this one is going to be a little more time consuming, so I'm just going to, instead of putting the positives, I'll just leave it as without a sign. So we have first differences are 46, 8, 6, 16, 14, negative 24, and negative 122. Obviously, first differences are not constant, therefore it's not linear. Go to second differences. Okay, so we're subtracting 8 minus 46, etc. So minus 38, minus 2, positive 10, negative 2, negative 38, negative 98. And you probably never saw this happen when we did, the jumping of the sign here, negative, positive, negative. Okay, so you can tell it's probably going to be a higher degree. Definitely not quadratic. Keep going. Third differences. So now it's like negative 2 minus negative 38 or plus 38. So that's positive 36, positive 12, negative 12, negative 36, negative 60. Okay, so third differences are not constant, therefore not a cubic, not degree 3. And hopefully, cross our fingers, we don't have to go much farther. So this time when we subtract 12 minus 36, is negative 24, negative 24, negative 24, and negative 24. So we got it to work. These are constant. So this is our value of c. C equals negative 24. So now we can now say that the degree of the polynomial from here is degree 4. So n is equal to 4. Degree equals 4. Which is n. B will just wait. And then we use our formula c equals a times n factorial. So the constant, negative 24, is equal to a. Now this time it's n is 4, so 4 factorial. Remember we did that, is up here. That's positive 24. It's always going to be positive. Okay, so this time when we divide by 24, we get a equals negative 1. Okay, so that means the leading coefficient is negative. Okay, so that's how we extend our finite differences to not just discover if a relation from a table of values is linear or positive, but we can keep going and look at cubic, quartic, and keep going. It's not too often where you get a question. I think the highest I would ever see would be like a degree 5, because you can see how much math is going on here, and it's not the most fun math. So make sure you put your signs in here. Just I see so many mistakes where students get the wrong sign or subtract with the wrong sign. Okay, so that's the lesson for today. We covered a lot of new stuff in terms of characteristics of polynomial functions, the end behavior. We're looking at the leading coefficient and the degree. We can figure out the end behavior. We can figure out the number of possible turning points, the number of possible x-intercepts, and then we can use that information to take an equation and come up with a potential sketch, or look at a graph and come up with a potential equation, etc. So and then the finite differences, if all you're given is a table of values, you can at least come up with the first term of the equation. So I didn't really do that here. So if I went back to this equation here, we know it's degree 3 with leading coefficient 1. So we know that this function is going to start off with the first term, f of x equals x cubed, and then some other terms which we don't know. I could look and see over here, well, the y-intercept is 0, so that means the constant is 0. And here, we know the leading coefficient is negative 1, and it's degree 4, so we know the first term is negative x to the 4th. Okay? Now, there is a way to actually keep going with this and be able to get the second term and the third term and actually get the entire equation. It's a really cool process. We're not actually going to be doing this in this course, but I used to teach how to do it in the math club. So if you're interested, I could talk to you about how you would do that. kind of interesting math. Okay, so that's it for today. Got some homework assigned at the bottom. So good luck with that and have a great day.